Cool. Can all the remote participants turn on their video if possible?
Yep. Here we are.
Awesome. Okay. Well, thanks everyone for coming back. So we have a couple of questions for you guys for a discussion panel. Hopefully we can get some interesting insights. So I'll start off with like a more high level question. So all of you guys, of course, are working on some kind of application that has something to do with safe autonomy, right? So I'm curious for your particular application areas, what would you say are like, or let's see if we can identify any like unifying roadblocks or like open problems that are really like key in preventing us from kind of safe deployment. And really kind of like more at maybe a more high level, what's the unifying set of objectives that we should really focus on, the field should focus on more generally in order to kind of push safe autonomy forward. If anyone wants to take a stab at that.
Maybe I can take an initial stab because I don't really have any real applications. So
Sure.
I'll start this more conceptually. I think that, I think one of the big challenges is just agreeing on a definition of what autonomy is and what safety means. And the obvious definitions of safety are like, I'm never going to crash or those just aren't realizable. We're never going to get to that point. So how do you soften those in a realistic way? And I'll defer to my colleagues who have more real hands-on applications to comment.
Do you want us to just jump in?
Yeah, sure.
All right. I totally agree. I was in a room with software safety assurance people, and I was trying to get them to understand that defining safe is really, really hard. That we went around for like 5 or 10 minutes of just iterating through avoidance, and they literally ended up at don't hit things. That was their requirement. The problem with autonomy is that we want it to go out into environments we didn't predict, and we want it to take actions that we didn't necessarily think of because we didn't necessarily think of that scenario, but we still want it to do the right thing. And that means that there are going to be times where, we want it to turn left, and there are going to be other times in what looks like the same scenario where we want it to turn right. And we don't necessarily know in advance which one is going to be needed at what time. And so I think there's a really huge amount of challenges just with defining what we want it to do in a way that simultaneously preserves the uncertainty and the ambiguity associated with the autonomy and defines the constraints that we really care about. I think that's a huge problem.
Maybe just to even further highlight like the nuance, even just don't hit things, that's not always going to be safe, right? If you're talking about human robot interaction, sometimes you want to gently hit each other, for when I'm using hit instead of contact, right? Or if I need to go through an open gate or go through a closed gate that'll open, I need to gently bump it, right? So even don't hit things, which seems obvious as a way to code safety, can have way more nuance depending on the situation. And
does it count if a whisker touches it? I mean, you kind of want the whiskers to touch it.
Yeah, I'm gonna give the most wishy-washy answer imaginable. I think it's when we know what maybe if we know it when we see it. If I am I don't know, either a program manager or I'm a person at a company is like, I'm going to buy this robot for my robot fleet, and I look at it and you tell me it meets some safety guarantees, but it's shaking around. Maybe this is a bias, but it looks unsafe to me. So I wonder what the human factors side of things, I say with no expert knowledge in this, what the human factor side of things people would say when they look at it and say, because would they be confident? At the end of the day, I guess some lawyer is going to be responsible for handling the litigation if something goes wrong. And I'm not sure, if we fully linked up barrier functions in law yet. I'm sure Aaron's on it though. But yeah, that's what I'm thinking of. That's what I think of.
Yeah, I mean, I think I'll add to this because I think Christian set that up nicely. I mean, I think first of all, we need to try to formalize what we mean of safety as best we can. with the understanding that it's going to be wrong inherently because we can't formalize everything. But we need to at least try. Because if we don't try, then we're totally flying blind. And then once we formalize, we'll find the holes in it, and we need to try to plug those. And it will be an iterative process where we try to fill all these things in a little bit. And I think that's a really important process to go under. The other 2 points in terms of the challenges, bottlenecks, important opportunities, I think related to this formalization is the need to have the communities talk to one another. So autonomy is something that cannot be done in isolation. The control theorists can't just design controllers, the roboticists can't just make robots do cool stuff, and the machine learning people can't just run through trenches of data till the cows come home, and then hope that on the back end, somehow all these pieces are going to magically come together and things will work, right? We need to start talking early and often and be open to criticism in our respective domains where we have our own blind spots. Again, I'm a control theorist sort of first, and I love mathematical formalisms, right? But how does that quantify sensor failure or uncertainty? I mean, Christian had a great talk where there was talking about that, but how can we really understand the real world uncertainties that are coming in? Machine learning, how do you add a little formalism to that, right? You can do all these areas and talk about places where they can be improved. And that improvement only happens if we come together and have an honest conversation trying to make things better, right? And then the final point is, once we have that conversation and we deploy these systems, I think a largely overlooked area, and Christian actually touched on this too, is the need for rigorous and explainable test and evaluation. This is very different from synthesis, totally different. So I think as roboticists, as control people, we always think about synthesizing. I want to make the robot walk. I want to make it be safe. But how do we evaluate that we've done what we need to do without the ability to change what's in the system, right? And so that sort of explainability, I think, is important as well.
So I'll jump in there and pile on. I agree with everything that was said. This is, really getting at the meat of things. And I'll almost up level it a little bit while secretly going down level at the same time. One important topic that was brought up, I think, in a couple of the talks, there's a semantic gap. There are two things here. There's how do you show your system is safe, and how do you convince someone else the system is safe? There's a gap between those things. And I'm a formal Methodist, so I'm all about math. But I know that if I write a specification in Z and I prove something in it, that does not convince the FAA that that system is safe. And so we have to look at how we bridge that conversation. We can come up with the best math in the world, but we want to make sure that we're creating a cogent and coherent argument. Additionally, this also was talked a little bit, what does it mean if it's a whisker, this or that? What is the acceptable level of risk for an operation? And that can be determined by the legacy operation, what's currently in the field, or if you're very lucky, you may have a blank, slate, tabula rasa. That being said, public acceptance is also going to drive what is acceptable. So if someone sees your robot wobbling, even though it's perfectly safe, that may not be an acceptable level of risk in the eye of the user or the person interacting with it, or for me, or aviation, third parties not connected to the operation. And they have a enormous legal clout. So liability is going to govern, who can get sued for these sorts of things. And lastly, requirements, being able to specify the requirements, big open thing. You've got a neural net, the data becomes part of the requirements. And I just really don't know how to tackle that. I'll stop there.
Well, let me just, please go on. No, I'm sorry. Let me posit an X Prize. We have those X Prizes, right? They're all fun. how about the people pleasing X Prize? You get 10 points if you please the lawyers with your formalism. You get 5 points if you please the customer. Basically you like it's almost like this might be one for the mathematicians that they throw it into some kind of simulated thing, and then you have a panel of people who say, I like this one, I like that one, and the winner has in effect given a practical description of safety, and just based upon what people by vote. And
we need to talk about your cost function. You give the lawyers double the weight of the people.
Maybe you have some insight in my brain right now, Nick. Yeah, that's my thought.
Yeah. But we've also got a problem with people, right? I was at a talk years ago now where someone from, I think, Georgia Tech was talking about they had an in-home support robot for someone who is paraplegic. And there was a Discovery special about it, and someone on the West Coast was like, oh, I volunteer. I want it to come to my house. So they brought the robot to the guy's house, and it was really successful at things like pull the blanket up in the middle of the night so he didn't have to call the nurse 5 times a night. And scratch the nose was a thing that he was able to do with it. And then he asked if the robot could shave him. And the researchers were like, maybe. And they covered the arms with padding and they did everything they could to make it safe. And he asked, is the robot going to be okay? Just not grasping that this was all for his benefit, not for the robot's benefit. There was a completely unreasonable level of trust going on. And so I think we need to be careful about safety, both in the sense of we are building it to be safe, but also in the sense of we are protecting the users when they have no idea that what they're doing is dangerous.
Yeah.
So it sounds like in all of this, the task specification problem is really a core problem. So, you know, I mean, is there any way that we can kind of, is the only way that we can refine our tasks via failure? Is there some way that we can kind of unify, like would this be solved if we got the lawyers, the control theorists, the formal methods people, and all the engineers, if we got them all into a room to kind of write down a formal problem for safe autonomy, like would this kind of solve this problem? Or do you think like there's always going to be some kind of inevitable failure that we're going to need to kind of grapple with online?
I mean, I've thought a lot about how to kind of define the concepts in the field of robotics so that we can do comparisons across things and we can map tasks to behaviors and things like that. And I don't think you should bring the lawyers and the users in until we have worked out what's going on inside our field. So my personal preference is for something more like the taxonomy of species or the Library of Congress cataloging system, where we go in and we define the structures of behaviors and tasks as they connect to each other. And then we bring the lawyers in and the users in, and we have them tell us what classification their problem is and help us iterate and fill in the gaps.
So yeah, I guess maybe let me amend my question a little bit. So I guess we have all these really diverse sets of communities, right? We have academia, we have many different applications in industry, and we have people, you know, in government making all these rules. What is like the appropriate or like the correct, if there is one, kind of place for each one of these people when it comes to, you know, designing these specifications, I suppose?
Well, when do they, this again might be a dodge. When do they normally get involved? When something's gone horribly wrong. And that's when they typically do, but we don't want that to be the case. I wonder, and maybe this is an unanswerable question, what are the things, and I'm not an expert in the history of safety and engineering, are the things that were safely rooted out in terms of regulations before something went wrong? Well, maybe it's impossible to tell because maybe things didn't go wrong. But what are the things that would fit that mold? And maybe we choose that instead of, say, you know, Hindenburg. You know,
Sure.
Yeah.
Well, I think the boat's already sailed on autonomy, right? I mean, we've already had deaths from it. I think we've crossed that Rubicon, as they say. So the question is, how do you prevent more, and how do you make things structurally better?
Maybe we can, you know, take inspiration from the autonomy stack perspective itself, right? Which is inspired from this layered architecture where you have, you know, your low-level tracking at the bottom, trajectory planning, higher level specification. You embody all of that and view that as its own kind of node that you can talk about. You know, people who reason about multi-agent interactions, and as you keep going up the stack, eventually you're abstracting things away where one stack is a city and another stack is a province or a state in a country, and that's, you know, the appropriate level of expertise then kind of becomes natural in terms of where you slot it in the stack. I think, you know, a point that Aaron made in his talk that was really fantastic was this idea that, you know, traditionally we've kind of worked in silos in these individual layers and in engineering and in government as well. there's very little communication between the two layers. And so this isn't an answer, but maybe we can take inspiration from this and have people leverage their core competencies, but also expand the communication across these different stacks so that the government is not making, for example, regulations without at least some kind of upward propagation of insights from, say, control theorists.
Yeah, I think that's as close to the right answer as I could get to, meaning that I think we would need to clearly understand where everything is fitting in a broader autonomy scope, understand it from a modular perspective, and then have assumed guarantee sort of contracts within that, whether it's legally or formally. I mean, again, from a control perspective, I can have a theorem that says this thing will absolutely 100% never violate safety, right? But of course, that theorem's premised on assumptions. The assumption is good sensing, right? Or other things. So, you can make internal guarantees in your area if you understand the information you're getting from other areas. And similarly with, a machine learning module, where you put it and how you put it in the system affects its ability to render something safe. So I do think that in the end, it has to be, this is how it's done, I think, in most industries. If you build a car, it's got a collection of thousands of components. The reason we have confidence that the 1,000 of components work is that they each individually were tested. And it's clear what their input-output relationship is with the rest of the car, whether it's a mechanical input out or a software input out. And if you meet those specifications, when you get an actuator for the motor control or whatever that has these things, it does this within these limits, the rest of the system will be okay. And that's ultimately what we'll have to build, is that big framework where you understand where your thing fits in the broader, context. How we do that is a whole nother thing, because this requires everyone to be honest about where their stuff should be. Not that it should solve all problems, right? Like as academics, we tend to want to think that our stuff will solve all those problems across all layers, but be a little bit realistic about where it fits in this architecture and being willing to work with other people to talk about where that will fit in. I think it's possible. I think those conversations are starting to happen now as we see autonomy deployed, because again, we're seeing where things can go wrong, and you would always rather things didn't, which forces people to talk a bit more, which I think is really awesome. And we're seeing more of this again with the learning plus control, or the perception, and a lot of these conversations across silos that I think is really encouraging.
We have a question from the audience, or well, not really. We have a question from Michael, but
yeah, I'm curious to hear thoughts from the panelists on how neural networks fit into this discussion. So in general, do we need to be developing verification techniques for neural networks? Do we need to be building wrappers around our neural networks? Do we need to not be using them? Just kind of want to hear everybody's thoughts from the various different perspectives.
Well, so I guess the first thing I'll say is not using them right now is not an option in autonomy stacks, right? At the very least, you need them for your vision and perception components. There's nothing that comes close to what they do. In terms of your other questions, right? I mean, I do think it really does come down to an architectural decision in terms of how you use them. It's if you are going to use them as part of a safety critical loop, you want it to be wrapped around with other things that can catch it when it fails, right? Because regardless as to how well we can verify it or whatever, there's always a risk of seeing some out of distribution input that just is well outside of the realm of anything you've done, and you have to be able to accommodate it. That being said, I think that also points to where, if you have the option, you should put this in the stack, right? These more sophisticated black box learning enabled components should go as high as possible in the stack, because you have a lot more, the farther up you go, the more kind of layers of reliability below you that can catch you if you fall. So.
Mm-hmm. Yeah, I'm sorry, go ahead. Somebody
I was just going to say, I didn't quite hear all the question. It's about learning.
Yeah, where should learning fit in the autonomy stack, if at all?
So
was the question.
I would like to push back a little bit, because in the last few years, I have worked on a program that has no learning in its autonomy stack. So there are systems out there that are high risk, that are very dependent on having minimal processor capability, and anything that learns would be verboten, from not necessarily from a technical standpoint, but from a getting approval to put it on the system in the first place standpoint.
Yeah.
My personal feeling is that it should fit where you need it, right? That you should use the minimal complexity thing that you need for whichever part of the system you're looking at. So if you need autonomy, if you need learning to do the job, then that's where you should put it.
Yeah, I second that. If you gave me a choice right now between an autonomy stack with learning or without, I would choose without if I wanted to make sure it operated properly. And I would use existing computer vision methods that don't require deep nets to do, distance measurement and things like that. I think in general, learning can, again, I've done learning high at the autonomy stack, self-supervised learning for vision. I've done it low at the real-time control level. I think the key is to understand where to put it in the stack and limit it to that right space. I mean, not to say, I'm going to say something kind of controversial, but I mean, learning is definitely overpromised relative to its ability to achieve autonomy. I hate to say it, but it's true. You can't do pixels to torque. It makes no sense. And it didn't make sense 5 years ago. It doesn't make sense now. But you can do pixels to a positional estimate with error bounds that you can put into your optimization layer that Christian's doing and put into your control layer and put wrappers around it and make sure everything's kind of contained. And that's where, again, learning does have, I mean, using data-driven methods has immense promise because we're going to have to use data. I'm not saying we shouldn't use data, but I'm saying we shouldn't black box the entire process and just cross our fingers and think if we get enough data, we'll have autonomous cars driving around. Architecture is everything. It's what we need to exploit. The same goes for control. I'm not going to have one control law that's going to run an entire car, right? It's going to sit as in one layer in a broader thing. So understanding where it should fit, how is the key consideration. And I think ultimately you need wrappers around any learning component, some sort of formal wrapper to make sure it doesn't exceed its bounds.
I guess I'll follow up your controversial statement with maybe another one, which is I don't think what you said is particularly controversial. Outside of like OpenAI, I don't think anybody's really advocating for pixels to torque anymore. I think everybody has converged to the message that you and our community or broad community has been saying, which is you need to take this more principled layered architectural perspective, and it has a place. But if you go pixels to torque, you're going to get yourself into trouble. So.
Yeah, and I'll jump in there and agree with that. Learning only when you need it, certainly for aviation applications, that's perception systems. Everything else has a solution that you can do conventionally. But there's an interesting fill-up there, and I'll throw this, and this might be a conventional or a controversial statement. One of the first ways we're going to see learning sneak into some of these high assurance systems is actually for systems which are currently very well understood and specified with boilerplate accuracy. So for instance, if I have an engine controller and I know exactly how to implement it in a deterministic fashion, but I think I can squeeze out a little extra performance by using some sort of neural net underneath it, I know exactly what specifications that weird black box thing is going to have to obey. And if it doesn't, and I can't prove it does, I turf it out. But if I can create the argument showing it meets the correct specifications of what that deterministic engine controller would do, well, then I've got my architectural solution. I have my neural net, I've got my deterministic controller, which is on top of it, running as a monitor, and I can always, of course, intervene when I feel it's going off the reservation. So I'm not sure if that's controversial to some people, but it may be a path in for some of these more interesting types of systems.
I'm reminded of, I think Aaron, I saw one of your students presenting the high-speed drone, the video you showed hitting up against the wall, and how I believe that was the paper that showed that there was a larger safe set. As long as you're within one safe set, you can go back to some others. You can go back to some other safe set as a catch. If I'm horribly butchering your student.
No, that's exactly right.
And so I analogize what was just said to that if you have some internal set that is like, oh, super goozing it, squeezing the toothpaste tube to grab get everything out of it, as long as it's out of that outer layer. That's how I analogize what was just said.
Yeah. No, I think that's a great analogy. And I think the earlier sentiments are also right. I mean, there's roles for this. If you have clearly defined specifications, it kind of goes back to what we were talking about. If you know the input output assume guarantee contracts, as long as it's meeting those contracts, you're good to go, whatever it is, right? And that gives you freedom within the module to do what you want because everything is so well specified outside of it.
sort of like you have the kids in the play, you have, I'm an analogy role, forgive me.
Go for it.
You have the kids on the playground doing crazy things, but you have the supervising adults watching them.
That's right.
You know, maybe get more fun out of what's going on with the kids running around. I say without kids, so who knows? But and as long as the adults are there, maybe it's a way you can leverage learning in this way that's being said.
Yep. Yeah, so just to bring it back to the first question, if the key challenge in safe autonomy, I would actually put as exactly this. It's architecture, but once you have the architecture, building the supervisors. How do we supervise individual modules running an autonomy stack or between it? What are those certificates? And that's an open problem that I think is hugely powerful.
Here's another question. So you're talking about the architecture, I guess, but do you think that we can actually maybe use the tools, for instance, you know, that we're kind of talking about, for instance, from robust control and estimation, or even like lists of desired task specifications that we might want to kind of achieve, or, you know, learned measures of risk, right? Or failures that we've seen. Can we actually use all of these kind of tools to actually automatically design systems or like hardware systems in the form of, you know, where should we place our actuators or where should we place our sensors in a way that like makes our, like, you know, overall system more amenable to safe usage? Do you think there's like a place for that?
I think about these all these formal synthesis methods that are from my colleagues here, and I just from the high level, I don't see why not. It's easy for me to say, but like each of these things have different properties for how well they're supposed to work under different conditions, and I can imagine daisy chaining these things all together. If it comes from, like, you're talking about building a system, the challenge is now I would dare say a mixed integer program, probably, right? You have these different components that are being swapped in. You can't have half a tire. Oh, you can, but you know, whatever. But I mean, that parallels a lot of discussions we have in robotics in general. You know, we spend a lot of time optimizing control. I mean, we've known how to do that for decades now very well. And people are like, oh, let's co-design the robot and the controller together. Awesome idea. It's just kind of hard. So in principle, yes, it's just hard.
Jumping on the kind of optimization analogy here, I think what this hints at too is the fact that ultimately all of this is this giant multi-objective optimization problem with this super complicated multi-dimensional Pareto surface that we just don't have a good way of navigating. And coming back to this idea of, you know, pixels to torque, for example, that lies at one end of this Pareto optimal curve, right? Which is, in principle, pixels to torque will squeeze out the best possible amount of performance because it can, as a special case, reproduce more modular designs. But it's really hard to say anything principled about how it's going to behave. So we introduce modularization, and this becomes this inherent kind of combinatorial integer valued optimization problem. Then if you know, even if you, let's say, come up with an architecture that you're happy with, and you say, okay, this can, you know, I can guarantee safety, it's okay with the trade-offs and in terms of performance, then you have to start thinking about, okay, but what are the assumptions that I had to put into place for my supervisors to actually be valid? So this adds another axis, right, which is how general is my solution? And you can just keep playing this game, and this becomes a super high dimensional problem where we really just don't have the tools yet in terms of how to navigate this effectively. But it's a super important problem and is ultimately probably going to be what's going to make or break whether we actually make autonomy something that's commonplace and ubiquitous.
There's so many directions I want to go from that comment. Yeah, I guess I think that my goal right now is just to be able to go in a principled way from anecdotal performance to reproducible performance to generalizable performance, and to have a conceptual space in which we can define what axis of the system design or environment we are generalizing along. Right? So we have this enormous giant spaghetti blob of multi-objective optimization problems. And It's like, I want to know, I have a robot and it's holding a rod and it wants to go through a door. Am I generalizing on the basis of where I hold the rod? Am I generalizing on the basis of how big the rod is? Am I generalizing on the basis of how big the door is? Am I generalizing on the basis of how good the robot's internal localization is? There's a ton of these factors, and I feel like if we could get a handle on the factors, that would enable us to start doing the research that we need to do to get a handle on the performance prediction, which would give us a handle on the generalizability that's really blocking the field right now.
And just to add to that one more time, architectures. When you have a large dimensional problem that's seemingly incredibly complex, the only way to simplify it is break it into small pieces that are more manageable. Break it up by time scale, by other scale. But architecture is everything for autonomy.
No, and I'll definitely second that comment. I think, you know, the astute deployment of architecture, even for things which aren't autonomy, is what enables really, really complex systems to be verified or validated, whichever side of the fence you're sitting on. So being able to identify the types of interactions that you're going to have, the independence of components, and being able to show what you can then, I don't want to say bootstrap, but what you can then reason from that particular allotment of functions and interactions and how you're composing things together becomes very, very important. Because if this becomes too complicated, there is the bugaboo, in at least in aviation, of unforeseen conditions. And if you do not have a correct grasp on what your foreseen operating environment is and what, you know, what is simply not understood, so what is unforeseen, where are the limits of your assumptions, you are going to have a very difficult time moving forward.
Great. Well, I realize we have one question from the remotes. Angelo, if you still have a question, could you unmute?
Yeah, thank you so much. Is it more of a comment or something for consideration? And I'd like to hear comments in response to it, because we talked a bit about trust before and trustworthiness. And I absolutely believe, whether it's by formal methods or by runtime, we can develop systems that are trustworthy. But whether or not they're trusted, it would be another thing. And the reason I say that is, if I get in an airplane that is piloted by a human, and the question comes down to, even though it's been verified and validated, what happens when it fails anyway? And with a human pilot, I have full confidence that they are going to, if the plane is going to go down, they're going to do their absolute best to try to land it, regardless of the corporate office mandates. They're going to try to land it so they can go home to their kids. In the case of an AI pilot, the AI pilot will be absolutely happy to put it in the side of a mountain, so to reduce the collateral damage on the ground. And that would be such an overriding matter of trust, is whose morality is the deciding factor of how the system fails. And before I turn it over to hear considerations on that, is Aaron, I've had enough pets. Those two poor robots really have to go outside. I know that pattern of walking around.
That's a good comment. I have not heard that before, but now that you mentioned it that way, I could.
Yeah, no, but thank you for letting me comment. And if anyone wants to expound on it or whatever.
I'll just start off, since I was already sort of talking. I think trustworthiness, I mean, explainability begets trustworthiness. So if you can't explain why something does something, you have a hard time trusting it. As you just said, you know why a human pilot will try to land the plane. You know, their motivation is hopefully clear. We assume it is, right? So I think this sort of notion of a morality for robots, if you'd like, is actually important, and not from a philosophical perspective, but from a practical one. I mean, I think most people here probably know, or at least should know, the 3 laws of robotics, right? A la Isaac Asimov. And the whole point there was every robot ever built had these 3 laws that governed whatever else was on them. It's sort of, it's this ultimate monitor, if you'd like, for our discussion, right? The thing that is between you and the robot are these 3 laws. It can't hurt a human, right? It has to do what it's told. It can't hurt itself. And we need to have describable specifications that at the final point when they reach the human are almost as easy to explain as this. So every time the robot does something, we can say it's doing it because of this reason and this is why. And I think that will build confidence and trust by having these clearly defined rules. If it's a big black box like an AI system, that's terrifying to me, you know. So we need to be able to explain and you know, trust but verify, or verify and trust, verify to trust.
But then you look at the people who buy Teslas and they put them on the road and they fall asleep in the back seat. I'm not actually certain that the users actually need explainability. I think that most of them would reject explainability.
It might be true.
I think the certifying agencies want explainability and the testers want explainability, but I'm not convinced that the users want explainability.
Yeah.
I think the users just want it to work, and they want it to work often enough that they don't have to feel concerned when they walk onto the airplane.
Mhm.
And I don't know, I think technically our biggest problem is going to be encoding the desired motivation into the decision-making of the robot. I mean, you look at a car, right? The difference between a nice, helpful, friendly autonomous car and a giant killing machine is a sign error in the goal function that controls acceleration when it sees a pedestrian. This is not something where we're embedding context and understanding into it. It's just down there in the guts of the code, there's a sign error, and now it's a giant killing machine. And I don't know how you take those ethical and moral issues and encode them in a system that has to meet, I have, you know, my sales team has told me that I have to deliver this product, and my lawyers have said we can accommodate this much money in legal fees. I just, and how you design it when you have a system where you're really constrained by cost and how much you can sell it for. That's a big gap for me. I don't know how we get there.
I'll lateral this over a bit. I mean, here we are at a robotics conference trying to have a really good faith discussion on what is a safe way to make robots in our world. But robotics, in the scheme of things, is still a young field. What about fields that have penetrated the popular sphere in our lives? Medicine. There are many people having very much not good faith discussions about medicine. The rampant pseudoscience that spreads about these things, about medicine, what you should and should not do. I mean, we all live this in a big way with the pandemic. What happens when robotics is a big part of our lives? And there are people who are so fomenting, like, oh, this robot just wants to kill you. And it sounds crazy. We're saying it, like I'm saying it sounds silly, but silly things have permeated the public consciousness. And we're talking about what the public trusts. While it is incredibly important that we approach this in a good faith way and do the best that we can, I fear that the era of robotic pseudoscience is coming. And that's something that I think, I don't know how close it is, but I think that when it starts to proliferate into our lives, that's when we'll start to see it poking out. So
I'll concretize this conversation and bring it back to the beginning point, and raise an interesting notion about trust, trustworthiness, the difference between, and how do you engender it. Flight data recorders. So the one thing that flight data recorders did was they established the ability to audit everything that happens in a flight. So as was brought up, the general public may not be interested, what lever the pilot's pulling. But the fellow from the NTSB, National Transportation Safety Board, who has to audit that accident, needs to be able to forensically reconstruct every decision that was made. And one of the things for AI is we don't know what needs to be recorded, or these autonomous systems. What do you need to know about the system state? What do you need to know about the intent? And what do you need to know about the available decision space for that particular function? And that is going to need to be recorded in some sort of fashion, at least in aviation. And if I don't miss my guess, it's going to proliferate into medicine. We work with the FDA very closely. And so insulin pumps are, of course, on our mind very greatly. And we're doing some stuff into self-driving cars through NHTSA and through a few other basically nuclear applications. But that's a whole other story. We won't go there. The ability to be able to capture the right things about the system and to know what those mean, so be able to interpret them, I think is going to become very important in building trust, because human beings were a lot happier to get onto planes when they knew, okay, the pilot would do everything to save them. And I'm not saying that the trolley problem is not the big thing, but the pilot certainly will do everything that saves them. But also the industry as a whole and the flying public as a whole knew, that accident occurred. We're now going to figure out why it happens, and we're going to make sure it never happens again. We'll write that regulation to get rid of it. And if you can't do that based on the fielded system, then you're going to have a problem.
Well, go ahead. And I think this should be the last question, just to keep everyone.
I want to ask a question. So about the safety, maybe just on the road. So this afternoon, maybe 3 to 4 hours ago, right in front of the convention center, there's fire truck alarm, and so that the fire truck is alarming, and the cars in front of them, they had to veer left or right to avoid the fire truck, so that the fire truck can go through the road fast. But maybe some of the cars before them veer left, and some of them veer right. So that the fire truck has to go left, right, and which didn't make itself faster than which didn't make it run very fast. And when it goes, so this means that maybe we need some coordination, but even but in that case, maybe one single person may not have the time and the information to do the coordination with other cars that is before the fire truck. And also another question is that so maybe this problem, how to save time for fire trucks, is already very, very difficult for humans, and also so maybe it's even more difficult for AIs. And for example, how do we set the constraints or barrier functions for an AI car that needs to avoid the fire truck, the alarming fire truck, to save time? So this is the red light, traffic light is red, and also you at the back you have a fire truck, and then you have to make your decisions to go left or right to leave the road to the fire truck, but also you need to keep yourself safe from colliding with the fire truck, and also you need to make sure that you try your best not to violate the traffic rules. So I mean, lots of things to consider. But or maybe you add this design sophisticated system to take that into account. Okay, so that you can efficiently avoid give road to the fire truck. But in this way, maybe a rare thing. It rarely happens, but once it happens, it's critical. So is it the worst thing to take this rare case into account? So and also, for example, what's the tool? Barrier functions? How to formulate the barrier functions for this, or other constraints? So maybe is this problem feasible? So yes, maybe my question is a bit messy. That's my question.
So I'm hearing questions of what should we prioritize in terms of what we accomplish? Like, should we make way for fire trucks and under what circumstances? And is it worth it, like, for steering the traffic? It's a question of priorities, and there's a question of how we enforce those priorities. That's what I'm hearing from your question. Is that fair?
And also, how do AIs take those factors into account? Currently, maybe they can avoid simple obstacles, keep away from walls, from other cars. But how do they avoid such fire trucks? So that might violate the traffic rules.
You're checking with current technology, or you how should it be done?
Yeah, let me, I can maybe, I heard it. I think I heard the whole thing.
Got it.
This is a good question, but, let me kind of step back for a second. So, you're asking a very complicated scenario where you have a fire truck and there's pedestrians, and what, which choice do you make? Do you go left, right? How do you prioritize those constraints? What if there's, machine learning modules or a vision failure? It's a very complex problem, right? I think the approach to any complex problem has to be stepping back and trying to peel away the levels of complexity. Anytime you approach a problem that's new, its complexity instantly explodes. So Christian can attest to this. Bipedal locomotion, seemingly simple thing on the back end, just like when we handle traffic situations, the actual ins and outs of it can be very complicated. Again, I would often get similar questions. Well, if the biped puts his foot there, how does it handle the balance and the inertia and the torso swing? And what happens if the actuator is not strong enough? Any engineering problem is very complex in all its intricacies, and that complexity is important and must be respected. At the same time, I think the art of being an engineer is to peel away that complexity, find the core problem, find the core specifications, right, and address them in a systematic and principled way. And in some sense, what I'm saying is we shouldn't try to answer that question that was asked in terms of how to actually handle that situation. What we should instead answer is, okay, what are the architectures for the autonomous system? What are its prioritization, decision-making protocols, right? How does it prioritize these different tasks? How do we come up with a way to do that more generally? And once we answer those questions, the rest of it will kind of follow, and from construction. So I am saying I appreciate the complexity of the question asked. It's a very good one. And I could give you a bunch of ways we've thought about things like this and tried to prioritize, for example, barrier functions, multiple barrier functions, subject to uncertainty with onboard vision. I could go on and on and on, but again, I think, especially for this panel and autonomy, it's about framing the problems in a way that we can attack it piece by piece and then put those solutions together.
See, I think I would take it further than that. So it's not just about defining your system, it's about defining the context in which your system is operating. If all the other cars on the street are also autonomous agents that you can communicate with, you have a very different solution to the problem than you do if they're humans and they are just reacting to what they see in front of them. If the emergency vehicle is an autonomous system, you have a different set of solutions to how you design the system. If a sensor is broken, or your maneuverability isn't great, or you're in the middle of a parade, or you're in the middle of a giant group of pedestrians, all of those contextual things are going to affect what you decide to do. And so you have to specify the problem clearly, and then your engineering solution will come out of that. But until you have those specifications, you can't really understand what the good engineering solution is.
Okay, if there are no additional comments, I think we should wrap it up there to respect everyone's time. I'd like to thank the panel once again.